So here's what we have to realize, guys, about a scale. Okay? And when you stand on a scale, there's a spring inside that you compress. Okay? When you compress the spring, what does the spring do? It pushes back. That's what the scale reads. The scale doesn't read how hard you're pushing on it. The scale reads how hard it's pushing back on you. So if I'm in an elevator, the reading on the scale is going to change depending on whether I'm moving up, down, accelerating up, accelerating down, or moving at a constant velocity, or being stationary. Okay? Their scale will change its reading depending on which one of those situations is true. Everybody follow me there? Okay, in which situation is it going to read my correct weight? And moving at a constant velocity. Okay, because in those situations, the net force is 0. So the force up and the force down are equal. Okay, if I'm accelerating upwards, it's going to tell me that I'm heavier. Because when I'm moving upwards, the floor pushes harder on my feet than it does when I'm stationary. That's how it moves me up. Everybody all right with that idea? Okay, so if I'm standing on this scale, okay, right now, and I'm blocking what it reads, okay, it's right now telling me my correct weight. But if I'm standing in an elevator, okay, and I'm moving upwards, it's going to, at least for a few seconds anyway, show me a greater weight. Because the floor is going to push harder on me. You've all felt that in an elevator, okay? The floor pushes on you a little bit as you accelerate up. Or if you're descending, you feel like, ooh, like you're almost like you're falling for a half a second, and that's it accelerating downwards. Okay? Don't look. Okay. I suppose there probably are. Most of them are either kilograms or pounds. So, okay. All right, does that sort of make sense to everybody? Okay, so that's what we have to visualize here, because sometimes what a question will give us is what we call the apparent weight. Okay, apparent weight is normal force. So sometimes you'll see it called that, especially in the next unit. We call it that all the time in the next unit. Okay, the normal force is the apparent weight of the object. Right. So in this case, the apparent weight of the person is 775 newtons. Their mass is 75 kilograms. What's their actual weight? Yeah, 730 is 38. Yeah. Okay. Point what? Oh, it's exactly 738. Okay. So their actual weight is 738. If the elevator was stationary or moving at a constant speed,
I think it's 735.
is it? I'll just double check. Yeah, 0.7. Okay, so there's their actual weight. If the elevator was stationary or moving at a constant velocity, which is what it does most of the time when it's moving at a constant velocity, okay, then that's what the scale would read. Okay, if the scale was descending, then this number would be smaller than this one. It's no different than the tension in the cable. Okay, normal force and the tension in the cable are effectively the same thing. They're the upward force on the elevator, person, occupant of the elevator, whatever. All right, everyone following me on that? All right, so can I calculate the net force now? Yeah, okay, so I just do sum of all forces. So 775 minus 735.75 is going to give us, what, 39.25? All right, so there's my net force, 39.25 newtons. And I can calculate the acceleration by going 39.25 divided by 75, okay, and we'll have our acceleration. All right, so this elevator is accelerating at 0.52 meters per second. Okay, upwards, yeah. Everybody all right with that? And it's just, I had forgotten to go over what the whole normal force and the scale reading had. I just noticed it because I was looking at our worksheet for today, and I was like, oh, right, I have those scale elevator on the scale questions. Okay, and I wouldn't have introduced that at all to you guys. So. Remember, the scale is reading how hard the floor pushes on my feet. That's an upward force. Okay, like when I step on the scale, I push down on the scale and the scale pushes. Only if I'm not moving, right? In this case, I'm accelerating, so it's pushing harder upwards than I'm pushing downwards on it. Yeah, does that make sense? So that's why it reads a higher number. I'm not pushing on it any differently than I did before. I still weigh the same amount, okay? But it's pushing harder on me because it's moving me. Yeah. No, I weigh the same. My weight doesn't change. How heavy I feel, my apparent weight changes. Yeah. No, G-force is apparent weight. Okay. If I'm pulling 2 Gs, I feel 2 times heavier than normal. I'm not. I'm still this heavy and this mass. That doesn't change. How heavy I feel changes as a result of my movement. All right. That's why we call it apparent weight versus real weight. Okay. I can go to the moon and weigh less. I would weigh less there because the force of gravity is different there. Does that make more sense? All right. Everyone okay with how that one worked? All right. So I want you guys working on today. So we did 1 and 2 yesterday, right? Okay. So I want you guys working on 3 and on. Okay. Actually, let's go 3, 4, and 5, and then we're going to go back to some inclined plane stuff after that. So 3, 4, and 5, then we're going to go back to inclined planes after that. So I'll blow it up a little bit bigger here. Okay, so try 3 and 4 and 5, and we'll talk about those ones, and then we'll go back to inclined planes. Okay, so the trick to number 4 is you got to read the question carefully. Okay, the fish is moving horizontally at a constant speed of 0.85 meters per second. What does that mean? There's no F net. Okay, the net force is 0 horizontally on the fish. It's also 0 vertically, but okay, we'll get to that. So we'll start out with, I was concentrating on sticking my tongue out. Okay. He's got a hook in his face. He's being reeled in by a fisherman. That would make me happy. Okay. So he's grumpy. Okay. All right. So we have this line here. It's 45 degrees, right? That's what, yeah. All right. So it's 45 degrees, and friction is opposing the force with 80 newtons. All right. We are looking for the tension in this line. All right. So it's really important that we first off make that realization that the net force here is 0. Because if the net force is 0 and there's 80 newtons going backwards, how many newtons are going forwards? 80. Can I calculate the tension in the line? Yeah, because now I know one side of that triangle. Okay, and again, there's nothing mathematically difficult about this question, but I have to get there with the context of the question. I first have to realize constant speed means no net force. That means the backward force and the forward force are equal. There's lots of little realizations that have to happen to get to the answer. Okay, so now that I have that 80 newtons, okay, it's the adjacent side. So I'm going to go tension equals 80 newtons divided by the cos of 45. Very similar to what I did in the last question mathematically. Okay, so 80 divided by the cos of 45. 113 newtons, okay, at 45 degrees from the horizontal. Now, usually when I write that answer on there, okay, people say to me, well, Coder, shouldn't this have 3 significant figures? Okay, my answer is this one shouldn't, and neither should this one. Okay, did I use the 45 to get it? Yeah, it's just a mistake, but I'm too lazy to change it on the key. 1.1 times 10 to the 2 newtons. Okay, the 45. Oh, sorry, no, it has 3. Sorry, this had 3. Sorry, it should have 3, and so should this. This should have 3. Should see. Sorry. What people do is they look at this number and make it 2. Why does this number not matter? You didn't use it. Yeah, it didn't affect your calculations. Okay, but the 45.0, this should be 45.0 here, but I'm too lazy to change the key. So, yeah. Okay, how many people have done 5? All right, I'm going to give you a few more minutes on 5 then. Okay, so there's 5. Give you a few more minutes on that one. So we got 2 workers pushing this crate along a level floor. All right, so we got our level floor, we got our crate. Okay, one person pushes with a force of 300 newtons and the other pushes with a force of 250 newtons. All right, so 300 newtons, okay, 250 newtons. Okay, friction opposes with 175 newtons. Okay, the crate is accelerating at 1.57 meters per second squared. Okay, what's the mass? All right, what do I need to find first? F net. Okay, I'm going to do that using m times a or sum of all forces. Sum of all forces. So 300 plus 250 minus 175, 400 and, sorry, no. 475, is that right? 375. 375 newtons. Okay, is my net force. All right, so there's my net force. It's obviously this direction. They didn't really tell me a direction, but that direction. Okay, so now I want to find the mass. Actually, direction doesn't matter here because mass is scalar, right? It doesn't have a direction. So, all right, so mass is going to equal then F net divided by acceleration. Okay, so our 375 divided by 1.57, and that'll get us our 239 kilograms. Okay, everybody all right with that? Okay. All right, now we're going to look back at some inclined plane stuff here. So okay, I want you guys to try that one. See how much inclined plane stuff you remember. I'll give you a couple of minutes and then we'll walk through that one together. So this one's about as simple as an inclined plane problem we'll get because there's only gravity and normal force that are involved here. There's no friction, no one's pulling the box up the ramp or anything like that. Okay, so what we have is our ramp. Okay, we know the angle of the ramp is 15 degrees and we have the box sitting on it. Okay, and so obviously the box is going to slide down the ramp because of these 2 forces. Gravity, which is always straight down. Okay, so we got Fg here, and normal force, which always acts straight out from the surface. Right? When I combine those 2 things, I get their vector sum, which is F parallel, and in this case also the net force, because there aren't any other forces other than gravity and normal force in this question. What I have to remember is that when I create this triangle, normal force and gravity are offset. And they're offset because I'm on a ramp, a 15-degree ramp. So this angle is always the same as the angle of the ramp. So now that I know that, I can calculate the force of gravity. Okay, so the force of gravity is going to be 5 times 9.81, so 49.05 newtons. And then I can calculate F parallel because I have the hypotenuse of this triangle. Gravity is always the hypotenuse of this triangle. And I have the angle. So if I'm going to find F parallel, then I'm going to have to go sine of 15 degrees, because F parallel is the opposite side, times the hypotenuse, 49.05. Okay, so we got 12 points, well, we only have 2 significant, well, sorry, we're not at that point yet. So 12.695 newtons is my F parallel. Right, now that I have that, and I know that it's also my net force, because there aren't any other forces acting, I can calculate my acceleration. F net, okay, divided by mass. So 12.695 divided by the 5 kilograms. Right, I get 2.5 meters per second squared. And what's wrong with what I wrote here? Down the ramp, downhill, down the incline. Okay, down is straight down, and that thing is obviously not going that way. All right, so it's this internal triangle that really matters. Okay, really, really matters, that internal triangle. It's the same for all of them. Okay, that'll help you to get F parallel. Once you've got F parallel, then what you want to do is put any other forces that are involved on the diagram. So I'm just going to redo this here just so I've got it clear. Okay, so we've got the box is going to be on here. Gravity is always going to be the hypotenuse. Normal force, which we'll rarely ever even calculate, is always that side. And F parallel is always this side. Okay, once you find F parallel, okay, then these forces have been accounted for. So what I do is I put F parallel on my diagram once I calculate it. Okay, then I add on any other forces. All the other forces are going to act along the ramp, right? If the box is sliding down the ramp, then friction will be acting up the ramp because friction always opposes. If it's a situation where I'm pulling the box up the ramp, then I would have my applied force here, and where does friction go then? Down the ramp. Okay? F parallel always points down the ramp. It's the vector sum of these. It can't do anything but pull down the ramp. Okay, so just keep in mind, because a lot of people make this mistake. Once you calculate F parallel, these forces are done. They should not be in your net force calculation. You already found their vector sum when you found F parallel. Okay. So as we said yesterday here, with the when I bank this, gravity pulls this way and normal force pulls this way instead of straight up and down. Because they're offset, this angle is this angle. Okay, and so then by law of similar triangles, this angle and that angle are the same. Follow me there? Okay. Like basically I'm saying like when the surface is level, normal force and gravity are equal. As soon as I start tipping one of them, normal force always pushes straight out. So whatever angle I tip it at is the angle they'll be offset by in the triangle. Yeah? Does that help anymore? That's really, I can't think of another way to explain it other than once they're not straight up with each other, whatever that angle is the angle this is going to be. Yeah.
So if you're pulling something up a ramp,
yeah,
and it's not frictionless, you have to account for F parallel and friction?
Right. So either the question would tell you what friction is, or once we've talked about how to calculate friction, okay, the force of friction is actually mu, which is the coefficient of friction, how sticky the surfaces are, multiplied by the normal force. That's when normal force will come into play. Okay, so then you would put friction on here, but we're not there yet. Yeah. Okay, so I'm going to put the inclined plane questions up here, and I want you guys, so we just did question number 1, so I want you guys to try, let's say 2, 3, and 4, and see how we do on those.